So now let's try to find the set of equations that is going to help us analyze one-dimensional kinematics with constant acceleration. Note, these can only be applied to acceleration where the acceleration is constant and not changing. For example, they will not apply in situations where we have, for example, a simple harmonic motion, which is like a swinging pendulum, or a raindrop falling against air resistance. The first things to consider here are what we call assumptions, and these are very, very important to know and to recognize. The assumptions include things like AX will be our representative of the x component of the acceleration vector. The acceleration vector could be positive or it could be negative. We will consider the initial particle's velocity, for example, at t equals 0 to be v0, and the initial particle's position to be x0. So our job is to find all possible v's and all possible x's for the positioning at any given time after the initial time. So that is our job. We have to find all possible equations of motions that can help us solve these problems. So first things first, and remember I told you that the initial conditions were really, really important. So our first initial condition is going to be what is happening at t equals 0 for any particle, and what happens at any given later time, which I'm going to call t. So let us assume that I've drawn a coordinate system, and since I'm only concerned with a one-dimensional motion, I am going to put my car or my particle or whatever I have at time t equals 0. Note, I didn't make a car. I could have easily made a car, or I could make a car with a person inside, or I could make a kitty cat in there. It doesn't matter. So my assumption is that there is something here that I know the initial conditions to, and then I will have some final conditions here. So my first initial condition is that at the x is going to be x0 at this point at t equals 0. And my initial condition is that velocity, which is the initial velocity, is going to be v0. At a later time, I am going to call this x as x, and I'm going to call this velocity as v. Some people like to call it vf and v initial and v final. It's up to you, whatever you would want to call it. I'm going to call it vf and xf, just so that I know that this is a final velocity. This is that time that I'm looking for. Okay? Well, where do I start from? What do I absolutely know? Well, I absolutely know that acceleration is defined, instantaneous acceleration is defined as delta v over delta t. Okay? That I know. Now, how can this help me? Well, I know calculus and I know derivatives. So in order to find the first equation of motion, I can simply take this to the other side, right? Multiply it with this, so it's going to be dA dt equals dv. Now, if I was to integrate both sides, where will my limits of integration be? Well, this is over t, so this will be from 0 to t, from initial to final, and this one will be from v0 to vf. If I was to rewrite this, since acceleration, remember we talked about this, acceleration is constant for our case. So in this way, it'll be at minus 0 equals vf minus v0. Or at equals vf minus v0. This is called the first equation of motion. Now to find the second equation of motion, we are going to use this, our first equation, and we are going to rewrite this as that. Oops, I called it v0, didn't I? I should call it that. Now, what is that? This one I know is not a function of time. So if I can take this over to this side, I can rewrite this equation as that. Why do I know this is not a function of time? Because that is what I have defined my initial conditions to be. This is a number right here. This is a number and this is a number. Why is that? Is because I need somewhere to start from. So in this case, what I'm going to do is I'm going to write at plus v naught equals dx over tt. Why is this not a number? The reason why this is not a number is because I did not define it to be a number. I just called it at any given time, right? At any time later on. This is what it's going to be. But I know for a fact that it is going to be a function dx over dt. Okay? Now what can I do? I can multiply this on this side. So this implies, plus v0 dt will equal dx. Okay? Since this is a plane, they don't depend on each other, I can rearrange this and write at dt plus v naught dt equal dx. And I'm going to integrate. Same way, what are the limits of integration going to be? So for this one, it's going to be 0 to t. For this one, it's going to be 0 to t. And for this one, it's going to be x0 to some final x. Integrate, a is constant, it can come out. V naught is a number, which is constant, it can come out. So that implies that a t dt plus v naught t gives me x. Integral dt will give me dx from the function x0 to whatever x final I called it, right? If I'm integrating this one, it's going to give me a t squared divided by 2 plus v naught t gives me x minus x naught, which I can rewrite this as delta x, right? This is my second equation of motion. Number 2. Done. Now for my third equation of motion, I'm going to start with what I know. What I know is a equals dv over dt. I'm going to rewrite this as dx. I'm going to multiply and divide both sides with dx. So this becomes dx over dx, right? I can rewrite this as dv over dx dot dx over dt by a simple rearrangement. So I just divided this with that and that with that. So I just rearranged it slightly. Take a second to think about it if it doesn't make sense. And this dx over dt can also be written as v. So this is going to be a over a dx equals v dv. So rearranging this one again, a dx will become v dv, which I can integrate and integrate. This is dx integration, so that will become x to x naught to x, f, I called it xf, and this one will become v naught to v final. Okay? Again, a is a constant, it doesn't depend on the x, so a can come out, and this way I will get a dx, x naught to xf, equals v squared over 2 from the limit vf to v naught. So the integration of that will become a xf minus x naught. So I'm missing a couple of integration steps in the middle here. I hope everybody is able to follow that through. Equals vf squared minus v naught squared divided by 2. Or I can rewrite this equation as 2a delta x equals vf squared minus v naught squared. And that is my third equation of motion. So 1, 2, 3. 3 equations of motion. Be very careful. You need to be able to derive these. And this written out is exactly those equations of motion. So remember the one we derived, first equation of motion? This one looks exactly like that equation, and the second one and the third one. Okay, so look at your paper, make sure that you're following along as we are going.